Well, the Frac is an episode of the Degrees of Freedom project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. First, mass. As defined by Wikipedia, mass is both a property of a physical body and a measure of its resistance to acceleration, a change in its state of motion when a Newton's force is applied. An object's mass also determines the strength of its gravitational attraction to other bodies. The SI unit of mass, the kilogram, was recently redefined. The National International Standards Organization got together and tried to define all the fundamental physical properties in terms of things that were inherent characteristics of the universe, not physical artifacts and place. So now, the kilogram is defined in terms of Planck's constant. Planck's constant is about 6.6 times 10 to the negative 34 kg meter squared per second. Or in other words, the kilogram is defined as the value of h divided by 6.62 times 10 to the minus 34 squared per second. That raises the question, what a meter is and what a second is. Well, for the curious, the second is defined as 9,192,631,770 times the unperturbed ground state hyperfine transition of the cesium-133 atom, and the meter is defined as 1 over 299,792,458 of the distance light travels in a vacuum in 1 second. So, the meter is defined in terms of the speed of light. The second is defined in terms of the vibration of the cesium-133 atom. The American engineering unit of mass, the pound mass, or the symbol Lb, sum m, is defined as 1 pound mass, is exactly 0.45359237 kg. The mole was discussed at length in the previous video. What is a mole? The most common moles are gram moles, also called moles, kilogram moles, also called kilomoles, pound moles, ton moles, and metric ton moles. Why do we insist on this different sort of moles? Because we're engineers and don't want to do more work than we have to. You should never convert mass in kilograms or pound mass to grams and then to gram moles. You should always use the kind of mole your mass is in. The conversion factor is simply the molecular weight. The molecular weight of methane is 16.0425 grams per gram mole, or 16.0425 kilogram per kilogram mole, or 16.0425 pounds per pound mole, or whatever mass units you have. 16.0425 mass units per that mass units mole. Why is this useful? Well, to calculate the pounds of oxygen with molecular weight 31.9988 required to completely burn 3 pounds mass of methane, we first write down the balanced chemical equation. Methane plus 2 oxygen goes to carbon dioxide plus 2 waters. That implies that you need 2 pound moles of oxygen for each pound mole of methane. It's the same expression in any other mole units. So now, to calculate the amount of oxygen, we need to take our 3 pound mass of methane, divided the molecular weight in pound mass per pound mole, and then multiply that by the ratio of the stoichiometric coefficients to get pound moles of oxygen per pound mole of methane, and then multiply that by the molecular weight of diatomic oxygen, 31.9988 pound mass of oxygen per pound mole of oxygen, and you get 11.9678 pound mass of oxygen. If you try this by converting things to grams and then gram moles, and then converting back to grams and then pound mass, you should end up with the same answer, perhaps with some rounding errors or transcription errors in it, but it would have been an awful lot more work. So calculating this sort of things any other way than using the mole unit that corresponds to a mass unit is just a waste of time and brain efforts.
Mass fractions and mole fraction. Mass fraction and mole fraction are used quite frequently in the chemical process industry, depending on what phase, solid, liquid, or vapor you're dealing with. One is more common than the other, but you will need to deal with both of them. X, Y, and Z are all used for mass and mole fractions. X sub A can be the mass fraction of species A or the mole fraction of species A. Likewise, for Y sub A and Z sub A, convention usually uses X for fractions in a solid or liquid mixture, Y for fractions in a gas mixture, and Z for the overall fraction in a gas-liquid, liquid-solid, or gas-solid mixture. It would be nice if we had different distinct symbols for these 6 different fractions, but we don't. We simply run out of variables in engineering. You have been warned. To convert from mass fractions to mole fractions, you need to take the species that you're interested in this case A. You divide the mass fraction by its molecular weight, and then divide the whole thing by the sum of individual mass fractions for each species divided by their molecular weights. To convert from mole fractions to mass fractions, You again start with the species of interest, A. You take the product of the mole fraction of species A and its molecular weight, and then divide the product by the sum of all the mole fractions that the individual species times their molecular weight. It might be worth your time to try to derive these formulas. For a binary, you could always use either of the formulas we just gave. They're not that laborious. But if you're one of those who really tries to minimize multiplications in your algorithms, you could use the additional relationships for binary mixtures linked on the website. One of the things that often has to be done when doing calculations is to determine an average molecular weight for something in a chemical process. There are two sorts of average molecular weights. The first is a mole average or number average molecular weight. It is given by the sum of the mole fractions of each species times its molecular weight, which can seem fairly obvious. You could also calculate it by taking the mass fraction of each species, dividing it by its molecular weight, summing those together, and then taking the reciprocal. It may take you a little bit to prove the formula, but it could come in handy. The mass average molecular weight is given as the sum of mass fractions of each species times their molecular weights. If you need a formula in terms of the mole fractions, you could take the sum of the mole fraction of each species times its molecular weight squared and divide that sum by the sum of the mole fraction of each species times its molecular weight. It may take a little longer to derive this formula. The mole average molecular weight is most often used for mixtures of gases. It's rare to have a mass average molecular weight for a mixture of gases. The mass average molecular weight is most often used for polymers, but it's also used quite commonly if you're processing a quantity of solids and occasionally with liquids. The takeaways from the video are 1. Materials and chemical processes are measured in mass, moles, or both. 2. Always use the mole corresponding to your mass unit. 3. You should be able to convert from mass fractions to mole fractions and back. 4. You should be able to calculate both mole average and mass average molecular weights of a mixture.
Thanks for watching. This video is brought to you by the DOFPro team.